Today I have a pleasure to invite you to participate in a webinar on what you always wanted to know about the p-value but were afraid to ask. Our speaker for the subject is Dr. Ulrich Dirnagl, the director of the QUEST, which stands for Quality, Ethics, Open Science and Translation Center for Transforming Biomedical Research at the Berlin Institute of Health in Germany. The presentation about the p-values will take approximately an hour, after which time we will break out for questions. But if you have any questions, you can type them in straight away in the question box on the GoToWebinar function panel at any point during the session. We will review them and respond to the questions in the time provided following the main presentation. And now I would like to invite Dr. Ulrich Dirnagl to introduce his topic and tell us all about the p-values that we wanted to know.
Okay. So, hello everybody. I hope you can hear me. And also you can see the screen, but yes, I can see it. So, maybe just one word about myself because it's relevant for the presentation. So I'm not a statistician. I'm actually a stroke researcher, mostly preclinical, and this is a field, and that's the reason why I got into thinking about statistics. This is a field where maybe 95% of the studies that are published find what they want to find. So in other words, they have a statistically significant result, which sounds good. But then if you look what turns out to get to patients in the sense that we develop better treatments from this, it's basically zero. And this is there are certainly many reasons for this, and we could talk about this quite a lot. But I won't do it today, just to mention that this could be because of internal and external validity. It could be because of the way the experiments are done and so forth. But when I started to think about this problem, I realized that at least some of this problem has to do with the way we do statistics, and in particular how we interpret the p-value. So it kind of started to make me skeptical about some of the things that I took for granted that I had learned in statistics class, basically. So that is actually my goal for today, to maybe make you also a bit skeptical, make you think. In an hour, I think there's certainly not enough time to really go into the depth of the problem, but my goal really is to rattle the cage a little bit, where many of us sit in a very comfortable position, but we should be, I think, more. We should think about what we do when we do statistics, and in particular what the p-value, which is kind of a pivotal element of the way we do statistics, what this actually means. So I have put my slides on the internet, so if you want to look up the references that I have, please download it at this address, which I will show at the end again. So now let me see. It's an interesting time to talk about these issues. Some of you may have heard about it. There is a kind of an upheaval. Even the Financial Times wrote about it, that scientists are kind of rising up against statistical tyranny. There have been a number of publications recently, some of them arguing that we should be more stringent about the p-value. Some even went further and said we should maybe stop testing in statistical testing, should give it up altogether. So this is a very active discussion, and we certainly will touch upon many of the issues that are being discussed there. Even the American Statistical Society has commented on this. They have recently they had a special issue even with, I think there were 42 articles in it, going through all the aspects of it, and this just tells us that even among the statisticians, this is an issue, and there's a lot of discussion about it. Interestingly, this whole discussion is actually not very new. In fact, when I started thinking about this, I bought this book on the left side, What If There Were No Significance Tests? Actually, I can still recommend it for those of you who want to dig deeper into this issue. There is a classical edition right now in paperback. So this was already in 1997. In 2007, there was this book, The Cult of Statistical Significance, all the arguments in there for laypersons. And recently I found a review that was written in 2000, and it was talking about an old and continuing controversy, and it made the point that actually from the moment on, like in the 20s or so, the null hypothesis significance testing and following the p-value were periodically heavily discussed, and so actually the discussion we're in right now is not new. It shows up, I think, with a cycle of maybe 10 years or so. So if we, just as a starter, I think what I would like to do is make you think about it. And we all read this or write the sentence, our results or the results in a paper that were significant at a p-value of, let's say, smaller 0.05. So many of you will have written it, all of you have read it. And what I would like you to do is to, well, maybe write down or at least think about it just for a moment, what the meaning of this sentence is. What does this tell us about the result, the hypothesis, the drug or whatever has been investigated, and then we say the finding was statistically significant at, let's say, 5%, at the 5% level. So what exactly do we mean by this? I think it's a fair question because, as I said, we write it and we read it. So everyone must have an idea about it. So just for a moment, please reflect on what this actually means, how you would explain it to maybe a student or to a friend. What does this mean? The reason why I want to do this is because in the end, when we come back to asking the question what it means, you can maybe check and see whether your idea has changed, your notion about it has changed. So what does it actually mean? I have asked this question. I give a lecture very similar to what we are discussing now, and it's not a webinar. There are people in the room, and I give them, I hand out a blank sheet of paper. First, they're a bit shocked because they think they have to pass a test, but there are no names on it. I just ask them to write down what this means. And interestingly, and not actually so surprisingly, what I get back is kind of a permutation of a sentence that I would phrase like the probability that I'm looking at a false positive result is below 5%. So this is an idea of what this means, that roughly 90% of those people that I ask, and sometimes there are even professors, but it doesn't really change much between professors, postdocs, and students. 90% of them have a paraphrase of this sentence, sometimes a bit more statistically phrased, but in essence, it's this, that this is kind of a false positive rate. There are other misconceptions, and they are also found on those sheets. Like there's the belief that P is the probability that our hypothesis is not true, which is kind of a false positive rate, or the drug doesn't work. It obviously depends on what you're testing. There is the belief that failing to achieve statistical significance is actually equivalent to demonstrating that it is not true. So you don't have a significant p-value, then you say, well, I've shown that my drug does not work, or the hypothesis is not true. There is quite often the belief that statistical significance has shows you some theoretical or practical significance of a finding, and also that a small p is evidence that results will be replicable. So in essence, if you want to boil it down to one sentence, there is kind of a belief that the p-value is equivalent to a false positive rate. Now, so we still don't know what p really is, but what I would like to do now is to, well, lead you on very thin ice, just thinking about the problem from very different angles, and you will be surprised which angles they are. So let me just throw in a few thoughts, a few facts, which at least might make us uneasy about those concepts that many of us have about the p-value. So let me start with what this paper calls a peculiar prevalence of p-values just below 0.05%. And in fact, there are, this is just one paper, there are many more in different domains. And what they generally show is if you look, if you just browse through papers and you write down p-values that you find in those papers, whatever they test, what you will see is that there is a sort of a continuum, which is what we would expect in terms of prevalence, numbers observed here. But what's very strange is that just below 0.05, there's kind of a peak. So they are very prevalent, and then it falls off again. So, well, we may have some idea about this, but whatever it is sort of strange. It's just an observation. Now, another psychological observation, and it's called the cliff effect. And again, this is an old study. It's a classic study, but in fact, it has been replicated, and it holds true. And what Rosenthal and colleagues, what they did is they presented a finding, a mock finding. They made up some statement and gave it a p-value. And then they showed this statement to scientists and asked them for their confidence in this statement. And the participants had to rate their confidence from 1, well, this must be true, to 0, no, I don't believe this. And what you can see is, and that's the cliff, is that as soon as a scientific statement is labeled with a p-value just below 0.05, confidence in the statement drops off from a very high confidence to a very low one. Again, that's a very peculiar observation, because I guess we all know that the 5% level is completely arbitrary. So why should our thinking about a statement have such a almost dichotomy here? Again, many of us will have an explanation for this, but it's just an observation that there is something strange going on. Now, here's another observation. Again, just from one paper, but there are other papers like this. So this is, I think, pretty robust. And what it shows is, first of all, that there are, this is just checking for negative results, or how many papers are reporting statistically significant findings. And what you can see is, first of all, that it's more likely, if you just randomly open a journal, that you will see a significant finding than a non-significant one. That's one thing. The other thing is that this is rising. So, and that is true for US, it's true for Europe. Asia has been always this is Asia, it always has been very positive. But lo and behold, what we see is a very high prevalence of positive findings, what they call the disappearance of the negative ones, and that this is going up, which again is a bit strange, but let's just kind of take a note and continue with finding evidence for that there is something strange going on. Now here's something else. That's on the same vein, basically. That's from my field. That's a systematic review from stroke research. Each data point here, these are studies. So the authors from Malcolm McLeod's group, Emily Senna, they were systematically looking at 525 preclinical papers in the stroke field. So this is mostly rat and mouse experiments. And in only 2%, the finding was a non-significant effect on the main outcome, which in these studies is infarct volume. So this is weird. So this is a field, I mentioned this, I think in the beginning, this is a field where everything's statistically significant. Again, just let's take note, there is something strange going on. Now here's something else. This is a typical finding. You see stuff like that, I guess, in the literature quite often. It doesn't really matter what it is, but I'll tell you, first of all, I made it up, but it's infarct volume. That's a measure that in my field is often used as a robust measure of the effect of a drug, which we, of course, give to try to reduce infarcts in animal models. Now, this is a bar graph, and it's quite common to use these bar graphs. You see quite a substantial reduction. That looks good. I mean, that's what we are looking for, drugs that reduce stroke damage. And you also see an asterisk, which tells us that this was statistically significant and that this, with the standard errors of the mean, this looks really robust. And this is a drug that I think make me very confident that we should further investigate this. Now, let me show you another way of graphing the same data. So this is exactly the same data. This is the way actually we should show such data. But unfortunately, we don't see this too often. So we see all the data points here. These are the individual animals with their infarct sizes. We also see a box plot with a range. We see the median and so forth. And the first thing I think we observe, at least I observe, is that it no longer looks that spectacular. In fact, you can already see that there are only a few data points that don't overlap, and that there is a huge spread which is completely masked by using the SEMs. It also now, in this case, it told us that the p-value is smaller than 0.005. And now it tells us that it actually was 0.047, so it was close to what we call statistically significance at the 5% level. So that is already one thing that, well, I think is noteworthy. But now, if you look at this graph, it looks conspicuously similar than the one we have just seen. What is different and immediately apparent is that there an asterisk is missing over the treatment. Why is it missing? Again, I'll show you the way this data should be graphed. And what I did is I just kicked out one data point, one extreme data point from the control group, and suddenly it was no longer statistically significant. So it's we would see a non-significant over it in a paper. Sometimes you see graphs like this, and people use it to show that the control doesn't do anything. So when they want to have no effect, this could be used like this. So again, just taking one data point out completely changed the picture from significant to non-significant, and actually the effect size before was 30%, and this is we have shown this in a recent paper with simulations. So in a scenario like this, if you take out one of the outliers, you usually end up with an effect, with a significant effect, even if there is none, and with a effect size of about 30%, which, by the way, is what we see in most of those studies, at least in the stroke field. Now, again, I mean, you might wonder, I mean, what is he doing? I mean, aren't we talking about p-values? So I'm just collecting evidence that there is something strange going on, something that we need to explain when we think about p-values. Now, here's my last example. You might consider it weird, but please follow me on it. Let's say you are a scientist who wants to investigate the hypothesis that telepathy exists. Well, I guess that most of us don't do this for a living, but let's just consider this is what we wanted to do. Investigate whether thoughts can be transmitted between persons. Now, we are scientists, and there are many ways of doing an experiment that investigate such a paranormal phenomenon, but one could be, for example, to use a deck of cards, and that's, as you know, has 50 cards, and the half of them are black, half of them are red, 25 and 25. Now, we could come up with a setup, a very controlled setup, where we have one subject drawing from this deck cards, card by card, and looking at the card color and then trying to transmit the color to a person in another room. And because this is a very controlled experiment, let's say this is far away, and it's a shielded room. There are no tricks to be played. So this is a very well performed experiment. And in this room there is a person B, and the person B is trying to guess the color that subject A is looking at. So what color is transmitted via telepathy? Now, I give you, so the experiment has been done. Let's just argue that. And so I give you the result, and the result was that the correct color was chosen by subject B in 33 of 50 times. And that is significant. That's a significant result. And it's, if you want the p-value, it's a p-value of 0.035. And if you now ask, if I would ask you now, I mean, do you now believe in telepathy? Because this is a significant result, and the p-value is even, well, it's well below 0.05. You'd maybe not even laugh. You'd say, you're crazy. This is stupid. I don't believe it. Now the question is, and that I think is the interesting point here, is why don't you believe it? In a class environment, when I ask people, I get lots of comments. People are scratching their head, and they come up with ideas why they don't believe it. They usually say something like this: well, is this the right test, or this is just one experiment, we have to do it many times, and so forth. Well, that's true, this could be done many times, but I then argue that, well, in essence, this is a setup that is very similar to what many people do in their lab, and then they would even say that they have done something 50 times. So it's actually not, so that's something I just have to submit to you. The reason why we don't believe this to be true, or that we are not convinced by such an experiment or such a p-value, is the fact that we don't believe in telepathy. In fact, we know that telepathy does not exist. So the prior of this hypothesis is basically zero. I mean, you cannot demonstrate the absence of telepathy, but we don't believe it, and there is no evidence for it. And so, if someone tells you with whatever p-value the p-value would be, you'd say there must be something wrong. What I normally also then kind of ask my audience, many of them doing experiments, I don't know, Western blots, animal experiments, whatever, and I ask them, why do you believe your own p-values? Why are you convinced by your own p-values? And what this brings up, and this is the reason why I use this example, is that in a strange way, our previous knowledge about the likelihood of a hypothesis somehow affects our trust in this concept of statistical significance. And in fact, since most of the things we test statistically we want to be true, we seem to be convinced that this must be true, and when this adds proof to what we have. But as soon as we test something that is where we know it's not true, this completely collapses. So we will return to this. This can be treated formally, but I think it's an indication that somehow prior probability of a hypothesis affects how we must interpret p-values, and that's something that is not normally written in textbooks, at least the ones that I have used when I was in statistics class, and my statistics teachers never brought this up. So we're still not haven't done any formal definition of a p-value, but at this point, I hope it's you are with me in having a feeling that we should really look into the p-value and what does statistically significance really mean. So just a short break. I need a sip, because now let's see what the statisticians say about this. So what is a p-value, and how can it be interpreted? So if you look up a statistics book, this is a common definition. Must be true. In fact, it is true. It's from a statistics book, and it says if we were to repeat the analysis many times using new data each time, and if the null hypothesis were really true, then on only 5% of those occasions would be falsely rejected. Now, in a few minutes, we will talk about the null hypothesis, but I guess most of us, well, can understand what this basically means. But there's a part in this sentence which, at least I have to admit, I have always overlooked, and that is, and if the null hypothesis were really true. So this is a first problem of this definition, because if we would know that the null hypothesis is actually true, we would not need to do any tests. So it's kind of it's a conundrum. It's a problem. We don't know it. And another way of phrasing or interpreting a p-value is also from statisticians, is to say that the p-value represents the probability of getting data as extreme as our results if the null hypothesis were true. Just as an interaction, the null hypothesis, for those of you who don't know what it is, I'll come back to it, is the opposite of what we want to show, is that there is no effect, that the drug doesn't work, that your hypothesis is not true. So so this definition is looking at it from the data distribution side. It's also, I guess, well, we can understand it, but before we challenge this, or in fact try to get closer to how we can interpret this in a real life situation and not in a textbook, we need to shortly talk about the null hypothesis, because it gets us to alpha, to beta, and the p-value, and then we can really sort of lift the hood. Now, the whole background of this thing, of course, and this is a very short summary, is that in statistics, test statistics at least, is there because we take samples, and those samples are samples. They are not the whole population. They are a part of it, and we are not usually interested in the sample per se, but we really want to make inferences about the population. You may, I don't know, study 8 mice, but in the end, you're not really interested in those 8 mice. You're interested in the population of this, let's say, particular mouse strain. If you do human studies, you recruit patients, and in the end, you want to make an inference about the population from which those patients come from. Now, the issue here is that we would like to have an objective method that helps us to decide whether an observation from this sample justifies the acceptance of a hypothesis about the population. So let's say there is a population, and we randomize patients, we give them an antihypertensive drug, and one group we don't treat with the hypertensive drug, they get a placebo. And then we want to see whether the drug, the intervention that we gave, actually produced two new populations, one that has a lower blood pressure, one that has a unchanged blood pressure. And how can we, in an objective manner, decide that this has actually happened? Or otherwise, we might just, well, guess or drown in noise or whatever. So this is where this comes from. It's about decision making from our hypothesis testing, and guys like Fisher, Persson, Neyman started this early in the 20th century, and they came up with a kind of a formal way of analyzing data statistically. And a key element of this concept is the null hypothesis, and that's why I think just for a second, it's relevant that we review it. If we want to test whether two samples come from the same population, remember, just in my example, that's the same thing. So you want to see whether a drug works. If it did not work, it has not produced two populations, the one with a lower blood pressure, if this was a blood pressure lowering drug. And so we could come up with one hypothesis that there is no difference between those populations. That's the null hypothesis. That's why it's called null, obviously. And there's the alternative hypothesis, quite often also, spelled out as H1, that there is a difference. This is actually the one that we are interested in. Normally, we want to show that there is a difference, or whether there is a difference. And so it's a bit weird in a sense, because if, as a researcher, I want to show that, for example, a certain treatment has an effect, or that a theory is correct, we are supporting it by rejecting another hypothesis, and that's that there is no effect, or that it doesn't exist. So if we know that, we can go one step further and ask what kind of errors can we make in our inference from those from testing those hypotheses. And one obviously is that we reject the null, so that we think there is an effect, but there was actually no effect. So that obviously we call a false positive. The opposite to this, or the alternative to this, would be if we accept the null hypothesis. So we do not find a statistical significance, but actually they came from two populations. So the alternative hypothesis was true, which of course we call a false negative. So these are the two errors we can make, and these errors can be quantified. The type 1 error, the false positive, is quantified by alpha. I guess most of you know this, and we very often set it to 5%. And the type 2 error is quantified by beta. It's quite often ignored. Sometimes it's set, or often it's set to 0.2, which is not equivalent to the level of alpha. It would, if we would be afraid of a type 2 error as much as we're afraid of a type 1 error, we should set it to 0.05, but that's obviously not what's common practice. And one way of looking at type 2 error quantification at beta is to call it power, and that's 1 minus beta. So that's in the case of 0.2 would be a power of 0.8, 80%. And the way of conceptualizing this is to say that if you have a power of 80%, to detect an effect of a certain effect size, then in 80% of the cases, you will be able to detect it if it's there. And in 20%, you will miss it, and that's your false negative. If you have 95% power, in 95%, you will detect this effect if it's there. Okay, so that's as statistical actually as it gets. But now let's return to this textbook definition that we have heard about earlier, and just to read it again. So the textbook definition says if we were to repeat the analysis many times using new data each time, and if the null hypothesis, now we really know what it is, were really true, no effect, then on only 5% of those occasions we would reject it, falsely reject it. Now, the problem as an experimenter or as someone reading a paper actually is that it's a definition that's not really very helpful. What we would really like to know, that's the question we would like to answer, is if we observe a significant p-value after doing a single unbiased experiment, we don't do 100 experiments. If we have a significant p-value, whatever the level is of alpha, after doing a single unbiased experiment, what is the probability that our result is a false positive? And this is tricky. This is what many people think the p-value delivers, but we already collected some hints that this may not be the case, and in fact, it's also not the definition of the p-value, but we would like to have such a value, and that would be a true false positive rate. So how do we get to this value, which we are so much interested in? And again, just a short break. Okay, so unfortunately, it's not that easy. But deriving such a value is a very nice exercise because it tells us everything about alpha and beta and the prior probability of our hypothesis. And what I'm going to use is not formulas, but I'm rather using a cartoon, and that's a cartoon that was published in The Economist. It was actually in 2013 in an issue of The Economist that had on its title the headline "How Science Goes Wrong." It was an interesting edition of this magazine because it actually this is not written by scientists, but it was a mirror that they showed us, and they had all the arguments why we have a problem in science right now. And key to this problem, they argued, was our misunderstanding of the p-value. And this is the way how they explained it. And I think it's a very smart way of doing it. So I would like to do it with you. And it's something that I would recommend that you may even come back after a day or two if you have downloaded the presentation, and play with these with the assumptions that in there, and so that you sort of grasp the idea behind it. But in principle, it's very simple. So what's the idea here? So let's assume that we test 1,000 hypotheses. We could argue 1,000 drugs that are being tested or so. It's certainly clear that this is probably not done by one researcher, but in a field this could be even true. So let's think about 1,000 drugs that are being tested. Now, let's also assume there are a few assumptions in this. So let me give them to you. So let's assume that of these 1,000, and these are 1,000 squares in this box, one of these 1,000, 100 of those drugs actually work, or if you rather would like to think about hypotheses, 100 of these hypotheses are true and 900 are false, or the drug does not work. And I'll return to the question whether this 10% is a good assumption or not in a second, but let's just assume it for a moment. 10% actually true hypotheses. Two more assumptions in this. One is that we are working at a 5% level of alpha, our significance level. Many of us do this. And that we work with a power of 80%. I already mentioned it. It's not very often that we talk about power, but in clinical trials, for example, 80% power is the minimum if you want to go through regulatory approval for your study. And so it's kind of the minimum. It's the 5% equivalent in some way. And it somehow signals that we are less afraid or less interested in a type 2 error than we are in a type 1 error, because it's less stringent. Okay, now we have all the assumptions that we need to explore what happens. And what happens is the following. So if we have 900 hypotheses that are actually true, and we work at a 5% type 1 error level, that was one of our assumptions, it's quite clear that we will end up with 45 false positives. And they have now marked them in this darker color. So these are the 45 false positives. 5% of 900, that's 45. This is this block here. Now, of the 100 that where the drug works or where the hypothesis is true, remember we work at an 80% power, so we are able to detect 80 of them, and we will miss 20. These are the false negatives, and they are now labeled in red. So now we can look at the result, and something very interesting happens. They call it the new true. So the new true, they have binned the ones where we have a significant p-value, because remember, p smaller 0.05. So these are 125 statistically significant results, drugs that we have found to be significantly different from the control. But if you look at it, 45 of which are false positives. Now this is the whole, I think the most important point of this graph. It demonstrates to you that it's not 5% false positives, it's closer to 40%. Why? Because power plays a role and the prior probability of our hypothesis plays a role. There's another very interesting observation to be made from this graph. So while the statistically significant results are in that sense not very robust, in fact, close to 40% are false positives, the negative results are much more robust in the sense that only a very small percentage of them are false negatives. So you could argue that in this scenario, a negative result is very useful maybe even more useful than the positive one, because you can trust it. It shows a true negative. Now, what this shows is that you can only interpret a p-value if you know about power, if you know the power, and that is doable. Most of us don't do it, but we can come up with it a priori. We should come up with it a priori. But it also very strongly depends, and that is the key message here. It also very strongly depends on the prior probability of the hypothesis, or the probability that the drug in this particular case works. And that's something that we can simulate in such a cartoon, which is nice for demonstration purposes, but it's obviously impossible in real life. And because this is, I mean, we do these experiments because we don't know. So you might argue that this looks particularly bad because it's a 10% prior probability that was part of it. So I invite you to play with it a little bit, and later on change it to 20 to 30 to 40%, and you will still see that this is has a big effect on how much you can trust your p-value to really demonstrate or show you a true effect. But it may also be an interesting reflection for many of us to think for a moment how likely our hypotheses are. So when I talk to researchers, very often they admit or they say that they think their hypotheses are quite likely, like, well, some say 70, 80%. And that's understandable because, well, if you think that's something very unlikely, you'd be crazy or maybe even stupid to spend 3 years with a PhD on it, just to demonstrate that it was like, I knew it. It's not true. So for a good reason, we have a bias towards our hypothesis or the drug that we investigate. But if you think this a little bit further, you should not be too proud about very likely hypothesis that you're testing, because it might indicate that you're a pretty boring scientist. So you're not pushing the envelope. You're testing things that where we already have a very strong basis for knowing what the next step will be. So it's very incremental, and we're actually not really probing into something really new. So the 10% are actually not even very radical. In fact, you could argue that in many fields, the true discoveries are even less likely. Otherwise, they would have been already known. And some people claim that for the interesting hypothesis, it's even lower than 10%. It may be in the percent range or below that. But in the end, we won't know. I'm just telling you this and spending so much time on it because I think with this graph, with this representation, we can get a grasp on the relevance of the prior probability of the hypothesis on our interpretation of the p-value. Now, maybe we should spend a few minutes on the power side of it, because it was mentioned, and many of us don't really talk about it much. It turns out, and this is a paper that I really recommend because it has been criticized for various reasons. But what's really good about it is that it has a very good theoretical treatment of the problem. But what Catherine Button shows in this paper is that in the neurosciences, at least, there's a rather low power generally to detect at least even large effects. And they found 20% power, which would be, I mean, insane, because throwing a coin has basically 50% power. There's newer literature and other papers on this. This is from a paper from Ioannidis' group, demonstrating again that the degrees of freedom, that's basically the sample sizes, are very low, or that's directly related to power, of course. And so they were looking at detectable effect sizes, and they found that 80%, if you just look at 80% of the papers or the studies, they have power that is around the level of throwing coins to show medium size effects. So generally, I think it's fair to say that power is extremely low in many fields. That we also have found this in systematic reviews in our field, in stroke research, but also in cancer. And there is an additional problem, which I just briefly mentioned, and that is the so-called winner's curse. And that's it hits you even if you have a true effect. The winner's curse, and there's a very nice paper by David Colquhoun, which has also R code in it, to do simulations like this and get a feeling for it. But the winner's curse, what it basically says is that if you work with low power, you're just able to look at to find the large effect sizes. So it's like if you think about microscopes, you have a very low magnification. You can only look at large objects. And with a power of around 0.5, let's just look at this 0.5 here, you will overestimate true effect sizes. Remember, these are true effects. So if you have a true effect, you will necessarily overestimate it by approximately 40 to 50%. So that's another effect that comes in if power is low. And that is another reason why we should be looking into power. Now, what I've just told you is, I mean, the problem of prior probability, the problem of non-stringent alpha and beta, and these are main arguments of this famous paper of John Ioannidis, which is, I guess, one of the most highly cited papers in biomedicine, and also one reason why it has never been really refuted in any sense, because from a very theoretical standpoint, and that's a very theoretical paper, you can argue that probably more than 50% of the published research findings must be false. Now, let me just give you one example from a totally different perspective, which you, especially if you have a medical background, may help you to understand the issue of the prior probability. Now let's argue, or let's think about disease screening. And let's argue that we have a very sensitive and a very specific test. So it has very low false positives and very false negatives, let's say 0.1%. And it's a screening for a very deadly disease. Now let's say you are taking the test and the test comes out positive. Now that sounds like a catastrophe. And obviously the question is, what is the probability that you have the disease? Now, if I do that in a class situation, I get all kinds of hands raised, and many will say 99.9% or so, and some come up with strange numbers where I don't know where they get them from. But the point here is, and those of you with a medical background will this, and there's always some medical people there, they will immediately say, I can't tell you because you have to tell me what the prevalence of the disease is. Now, if I tell you that the prevalence of the disease is 1 in 50,000, one person in 50,000 has it, then it's very easy. Then you can calculate it. You have a false positive rate of 1 in 1,000. With a prevalence of 1 in 50,000, this means that the probability that you have the disease is 1 in 50, not 99.9%. So now, why am I showing you this? Because the null, you do not have the disease, started with a very low probability. And in fact, specificity and sensitivity are closely related to type 1 and type 2 error. In fact, type 1 error is basically 1 minus alpha. and sensitivity is very closely related to type 2 error. Sensitive tests have a very low type 2 error rate, and the incidence of the disease is related to the true hypothesis rate. So just, I mean, a completely, from left field, this is a completely different way of looking at it, but it's the same problem. You cannot interpret a screening test if you do not know the probability of or the prevalence of the disease, and this means you cannot interpret in this sense a p-value if you don't have the prior probability of your hypothesis. Now we're almost close to the end, but let me give you a little bit food for thought on top of that. So because of those issues that I was raising, the American Statistical Association recently released a statement, which I guess was a totally new thing for them. I'm not sure whether they ever had something like this. And it was on p-values. And they said, which I guess you now understand why they did it. They said a p-value does not provide a good measure of evidence regarding a model or a hypothesis. Now, is this true? I mean, isn't this against what we normally, even from physics and from other domains, what we hear from others? So let me give you one example, and that's this guy is a physicist. It's always nice to look at physics. This is Peter Higgs. It's the guy who came up with the idea of the Higgs boson. He got a Nobel Prize for arguing that there must be such a particle. It was later on shown. And the guys who showed it, they used statistics to do it. They ran experiments and they came up with a extremely low barrier. So they were using what they call a 5 sigma. That's their 5% is a 5 sigma, and so they came up with a probability of around 3 times 10 to the minus 7 of what? So the new scientist said that there is a 5 in 10 million chance that the Higgs is a fluke. And if I was right in my argument, this cannot be true because you cannot talk about the Higgs that way. And in fact, again, it were the economists that gave the right interpretation. They said, this is not the probability that the Higgs boson doesn't exist. It is rather the inverse. It's the particle. If the particle doesn't exist, 1 in 3.5 million is the chance. An experiment just like the one announced this week would nevertheless come up with a result appearing to confirm it does exist. So that is very much close to the textbook definition. And it's the relevant thing here is that this probability is applied to the data, and the common fallacy is to apply it to the explanation, to the hypothesis. And I have one last example to illustrate what this really means, and then I guess you'll really understand it. Again, it comes from physics. It's nice to use physics because we usually consider them this is the hardest science we have. Some of you may remember that in 2011, there was a big thing on the news. It was a headline all over the place, New York Times titled, "Tiny neutrons may have broken cosmic speed limit." They even said, "Roll over Einstein." What happened? Well, again, at the CERN in Switzerland, they did a huge experiment. They produced neutrinos. They sent it on a very long journey, many hundreds of kilometers, even through mountains. And then they detected them somewhere in Italy, those neutrinos. And what they found is that they arrived a little bit earlier than they could have arrived if they travel at the speed of light. Now, this is obviously, I mean, this is insane. This is incredible. This is a new physics. Causality may no longer exist. I mean, this is a new physics. So this is the reason why there was this huge excitement. Einstein's theory of relativity would fall, and they knew that this is so insane, and so the prior is so low, they lowered the significance level to 6 sigma. They added 1 sigma on top, and they replicated the results, and they still found it to be significant at this level, and they published it. Now, this did not result in a Nobel Prize like it did with the Higgs. In fact, it resulted in a major embarrassment, because what happened was that their GPS system was not properly synchronized. That was something that came out when other physicists entered the stage and checked what they were doing. A cable was also loose, and now we are still left with Einstein. And what this, I think, very nicely shows us, that p-values are ignorant of simple systematic errors. And again, we cannot interpret them as a measure of the probability with which our research hypothesis is true, because the p-value not only tests the null hypothesis, it tests everything else in the experiment. So someone has said that at around p.05, the likelihood to make a fool of yourself is even higher than 5%. So where does this leave us? What's the conclusion? There are a few of them. Most of them I think I have mentioned in passing, but just to review them in the end. Do not believe that an association or effect exists just because it was statistically significant. Do not believe that an association or effect is absent because it was not statistically significant. Do not believe that your p-value gives the probability that chance alone produced the observed association or effect, or the probability that your test hypothesis is true. Do not conclude anything about scientific or practical importance based on statistical inference or lack thereof. P-values do not provide evidence regarding a model or hypothesis. We should think biological significance, effect size. We need to increase statistical power in general, and we need to replicate. Okay, I think this is all I wanted to say. There is a paper that I'm referencing here where I have very recently summed up and provided more references for what I was just saying, the references here. And I have, as I mentioned in the beginning, I have given my slides into onto a website, and this is the site where you can download it. And I hope that you are or have been provoked by some of what I said, that you will think about it, maybe even play a little bit with the graph that I've shown you from The Economist. And yeah, that's all I wanted to say. Thanks. I think there are questions now, but we'll see.
Hello, yes, thank you, Ulrich, for your presentation. I'm sure we had quite a few people interested, and also people inquiring about the availability of this talk later. So I just wanted to confirm for everybody that yes, this webinar is being recorded, and Eli will make it available later on our website. And now we can move on to some questions, particularly Cabello Mogalaboni has been very patiently waiting for an answer to a couple of questions. Apologies if I have mispronounced your name terribly. So the first question would be, how is p-value different from confidence intervals in terms of accuracy in reporting the result?
It's very different, because it's a very different thing. So the confidence interval is a, I guess, pretty smart way of demonstrating the spread of your data. It's a good way to show the spread of your data, and people have argued that it should be used instead of p-values. What you are referring to, I guess, is to use, you could be tempted to use confidence intervals as as a statistical test if for example the confidence intervals do not overlap. but then you have done something, you have done a test. The confidence interval is innocent, if you wish. It's descriptive statistics. It shows you the spread of your data. If you go one step further and then you use it in such a way that you, for example, check for non-overlapping and so forth, then you're basically performing a t-test, and then all the other things apply. So I guess that will be my answer to it. So use it as a measure of spread of your data to characterize your data. Use it in a descriptive fashion, but not as a test statistic.
Right. So we also have a related question. Is it accurate to report confidence intervals instead of p-value, or should I report both p-value and confidence intervals?
Well, I guess first of all, a lot of the journals would probably require something like formal statistical testing. And I have to admit that I'm not of the fraction that would argue that although I've been very critical about interpretation of p-values, I'm not part of the group that rises up and says we should completely give up on them. So I don't see this as an alternative, and that's in a way relates very much to the answer to the first question. I think confidence intervals, and that obviously is only true for certain types of data, is a nice way of showing your data and the spread of your data. If you want to do formal testing, well, do it. The question is how you interpret it, what kind of stringent alpha and beta levels you're using, and then the question is how you interpret it in the end. So I don't see this as either or. I mean, you can do both, but if you use the p-values, everything else, it's a statistical test that you do, and all the things that we have discussed apply. Whereas the confidence interval is much more innocent in that way. But there's no reason why this could not be combined if you do it properly.
Excellent, thank you. And I have now a couple of related questions to one another, so I'll read them out together. First one is asking, is Bayesian statistics the only alternative to frequentist statistic? And another question, I think that would be related, is about, does the Bayesian statistic overcome these problems when proper priors are used? Is that the future of statistics?
Yeah, that's an obvious, of course, a very relevant question, and in fact, I in a way, of course, triggered it by using a term like prior probability, and when I showed this graph from The Economist, I said we don't know the prior probability, and that, of course, is where Bayes statistics comes in. This is an alternative form to the frequentist statistics that most of us use. And the first question was, is this the only alternative? Well, as I admitted in the early on, I'm not a statistician. I only know those two major ways of doing statistics, and that's frequentist or null hypothesis significance testing and Bayes. Maybe there's a third one, but if there is one, is kind of undercover because we don't read about it or we don't hear about it. The interesting question, of course, is, can we use Bayes and overcome the problems that are so obvious when we talk about p-values and frequentist statistics? Well, that's a very contentious question, and there are people who would. There are Bayesians who would probably clearly say, well, yes, well, don't forget about frequentist, and this is why you had to talk so long about these things. If you should have spent the time in explaining Bayes statistics, this solves the problem, because maybe for those who are not familiar with it, Bayesian statistic actually comes up with with a way of phrasing confidence about your results that is exactly the way most people misunderstand the p-value. So Bayes comes up with a likelihood of a hypothesis being true, or a drug to work. And then you obviously, if you hear that, you say, well, let's use it. This is great. I mean, this is exactly what we need. There's a little problem, and the little problem is that with Bayes, you need to make assumptions about the prior probability. And this is where the big discussion starts and the big controversy starts. And there are kind of factions that fight each other, and there are sort of people in between. I don't know enough about both to really take sides. What my take on this is that, in fact, in most cases, it's, at least in the field that I work, it's very hard to defend the priors. Of course, you can come up with priors, but it's hard to defend them. And that's one thing. The other thing is about the Bayes factor. So in the p-value, so to speak, if you wish, of the Bayes statistics is called the Bayes factor, and that is a quantification of the confidence that you have in the hypothesis being true, in the drug being working. And so the higher the Bayes factor, the higher the trust that you have in there. I'm first of all, there's not time enough, and I'm certainly not the person to do it. But the Bayes factors have issues themselves. There was, I think, a recent very nice treatment of it by Uri Simonsson on his blog, and I would point you to that. So if you send me an email, I will point you to it. There's a very nice treatment of it. But taken together, I think there is no simple way of switching now just to another type of statistics. There are problems with Bayes as well. And we did some, we have done, for example, studies where we have compared both forms of statistics, especially if statistics, frequentist statistics is used in such a way that it is done in a sequential fashion, so that it is informed by prior experiments. There is not so much of a difference in, if you do simulations, there's so much difference in or so much you can gain. But the last thing I would say about it, I think the smart thing to me about Bayes statistics is that you are integrating, or you are able to integrate the results of an ongoing experiment, for example, into it. So your confidence is constantly being informed while you do an experiment. But having said that, I mean, I'm not sure in which field you work. There are fields where Bayes is well known and used in neuroimaging and psychology, certainly. But if I would come up in my field in stroke research with Bayesian statistics without frequentist, I would probably be not accepted by the referees because they don't understand it. So that is maybe a very practical consideration, but it is relevant because most people don't understand it, and they will just then argue, well, you're tricking them into something. So that's my take on it. It's a complex issue, and there are no miracles, I think, that where Bayes would now solve all those problems.
Excellent. So another question we have here from Sarah is, how do you determine beta or power? Is it arbitrary like the p-value?
Well, first of all, you have to set it. Before you start an experiment, you have to kind of decide what kind of a type 2 error you're going to accept. So if you say, well, if I add a certain effect size, which you determine by biological thinking and by the variance of your data, you need some pilot experiments, or you from the literature, and then you say, well, if I want to detect an effect size of 0.5, which would be half a standard error, and that's normally considered a medium-sized effect, I want to be able to detect such an effect at a certain power, let's say 80%. Then you know that in 20% you may have missed it. You could then argue, well, why don't I say 95%? That sounds much better. Then I will just miss 5% of those effects that have this particular effect size. But obviously this comes at a price, because you can only increase power by either decreasing the variance, which sometimes is possible, but sometimes it's just given. It's a variance, the biological variance of your experiment. Then the only way to change power is to increase your sample size. But the message here is you have to do this before you start the experiment, informed by the variance of your experiments and informed by a biological or medical or whatever consideration, what kinds of effects are relevant and need to be detected by me, which I do not want to miss. If I miss them, it's a catastrophe. So I need this type of power. So this is how it's determined. You determine it. You set it, and quite often, because the variance is quite substantial in most biological experiments, the bad news is that at 80%, at 95% or so, you are no longer able to use n equals of 8, which I just mentioned in passing, that 8 is in many fields, in vivo at least, in animal experiments, the standard sample size. If you work with sample sizes of 8, and you will never be able to get to a power of 80% and detect a small or medium-sized effect size. You need 30 animals or 30 subjects or so. But there are very nice programs to play with those numbers, and then it's you have to decide, can I do it?
Thank you. And another question here is when and where the p-value should be used, in your opinion?
That, of course, is an obvious question after bashing it, and then at the same time telling you I don't think it should be given up. First of all, it's one maybe what a guide what guides me, I think, in a is a sentence that I think it was ascribed even to Fisher or so, but I'm not sure, for the 5% level, and that's it's worth a look if it's 5%. So the idea here is to say it is p-values on the order that we normally use are kind of if they are the result of a well-designed experiment, of a well-powered experiment, are a way of kind of sifting through and making decisions in which direction to take our experiments further. And there is certainly a risk that we run into. That's the issue of the false positive. But if we combine the use of p-values, and that's another way I would phrase it, if we use p-values in a more stringent way with, let's say, 0.005, that's what another group of statisticians have argued for, to sort of be one order of magnitude more stringent, and then replicate those findings if they are pivotal, if they are critical, if they are relevant for what's coming next in a PhD, or taking something into a clinical development or so. If we then replicate it, ideally independently and ideally with greater power, then I think it's p-values help us to sift through the evidence that we are generating. We at some point need to make these decisions. There will be errors that we make, but we need to tune our interpretation and our alpha and beta in such a way that we are not just fooling ourselves in 50% of the cases, which is, I guess, what we are doing now. So yes, p-values can, in a proper experimental design with stringent thresholds, help us to make decisions. That's where I would use them.
Excellent, thank you. And I think we could close with a question. So you mentioned already a few times that you are not, whilst you're critical of it, you're not one of the propagators of the idea of dismissing the p-values altogether. And I wonder, what is your take on potential consequences of what would happen if the p-values were to be completely abandoned?
Yeah. I mean, there's now a controversy that's raging about it. I take sides with John Ioannidis. He has written, I think it was in JAMA, a nice piece on it, where he explores these consequences. And in a nutshell, what he says, and I think he's right, we are already drowning in false positives and hilarious claims made from experiments with non-stringent alpha levels, low power and bias. If we let go and say, well, no more tests, no more statistical tests, this is the end of it. I mean, we will be awash in, I think he called it, nonsense will reign. Everyone can claim everything by just saying, well, we did this in this experiment and look at it, this looks good, we believe in it. So in one sentence, I think if we give up on this and we will be drowning. We are already, I think, staying hardly above water level, but we will be certainly drowning if we completely give up on it.
Thank you. With this, I suppose we can close the official part. Before everybody leaves the meeting, and before I thank Ulrich for his fantastic presentation, I also wanted to ask all of you who have remained with us until now, if you could just let us know how do you feel about the webinar, and did you learn what you expected today from the presentation and the question and answer session. So if you can just check the little poll that should have popped up on your screen and choose one of the answers, that would be very helpful for us and I hope for Ulrich as well, in terms of understanding what other events we might be organizing of similar kind in the future. Yeah, so again, if you could just tell us to what extent has this webinar met your expectations, that would be very helpful for us to gauge how worthwhile this exercise has been. I can see that most of you have already voted. I think there is a couple of people who are still that we are still waiting to hear from, and in a few seconds I will be very happy to display and share the results with everybody so you'll be able to see. Okay, excellent. Thank you very much. So I'm closing the poll now, and I'm happy to share the results. I'm very glad that most of you had your expectations met, at least to some extent. That's very, very great for us to know, and we hope that we'll be able to meet your expectations with events in the future. So now nothing else remains to do except for obviously thank you, Ulrich, for your presentation and for taking on all the questions. It's obviously a subject that has been a subject of many controversies recently. So it's really great to have such a thorough review of it, and obviously also learn about your own take on the current discussions.
Okay, thank you.
Thank you.
Bye.